Okay. Are y'all ready for this? Aww. I think it's...
Yes.
Okay. It still doesn't want to come out of the... It's too much of a trial too in the video. Yay!
Yes! It's like not coming out. Oh. What?
Well, now we're basically going to look at the forces behind the trebuchet, or what makes a trebuchet a trebuchet. A trebuchet is just a first-class lever, and is classified as that because it has a fulcrum point. So you could think of like a teeter-totter. Teeter-totter has two counterweights that are harnessing the free fall motion of gravity in order to have, fun, whatever, at a playground or something. But a first-class lever for a trebuchet is, instead of just lifting something up, is pretty much projecting something. It's throwing something up and over itself. So the main force involved in this, of course, is gravity. It's the only kind of power that the actual trebuchet would have, is using that counterweight in proportion to the projectile and harnessing that free fall motion of the weight of the object. So the force in newtons would be due to gravity, the mass of the counterweight times the gravitational pull towards Earth, 9.81 meters per second squared. Other forces after the trebuchet is in motion, so the gravity plus the pivot point, would be like centrifugal or centripetal force. So a centrifugal force would be from the point of view of the projectile, because it is being swung in a path up and out. A centripetal force would be from our point of view, watching this path as either the projectile or the gravity pulling on the counterweight is making that path, that spinning motion, if it were to continue. So that's when you see like trebuchets that have like the multiple spinning, where it spins and spins and then it projects after a while. So other forces might be torque. Torque is like a force in that there's a push and pull. You can think of torque as a twist. So it's a force that rotates, or is the tendency of a force to rotate an object about an axis. Because a trebuchet has a fulcrum, and because the counterweight is under gravity after the trigger mechanism is released, torque is working on the trebuchet to twist the trebuchet, to pull it down, to push it down. We wanted to prove that 45 degrees is the best angle to launch a projectile at. So we made three vectors, one at 20 degrees, one at 45 degrees, and one at 70 degrees, all having the same initial velocity of 10 meters per second. And then we just used kinematics formulas to find the horizontal distance and the vertical distance that each one would travel theoretically. So for the 20 degrees, we got it was 47 meters for the range and 140 meters for the height. For 45, it was 35 meters for the range, 157 meters for the height. And for 70 degrees, it was 17 meters for the range and 170 meters for the height. So anything below 45, you have a great range, but you're giving up some of your height. And anything above 45, you are giving up some of your range for maximum height. So 45 is the best angle measure, which achieves both maximum range and height. And then for ours, we found that our launch angle is about 43 degrees. And then we took a trial where we had, where our trebuchet shot an egg about 13 meters, and it took about 1.5 seconds for the whole trajectory. And so then we just plugged that information plus the idea about gravity and all that fun stuff into the kinematics formulas to find that our vertical component of velocity was 14.7 meters per second, and our horizontal was 8.7 meters per second. A peaceful town in the middle of nowhere. Victim number 1
I hate you.
slowly zooms in. Your face is ugly.
You're totally trying to hit me. Hold on. Okay, wait for it to focus. Okay, it's focused. Go! Oh, it's so intimidating! Where'd it go? Okay.